So that is the modeling of excitation system and performance analysis. Here, in terms of performance analysis, I will consider discussion on simplified model, and then the regulation of generator terminal voltage, and with the controller design. And then in fact I have one numerical example to discuss about the performance analysis for excitation system. So basically what you understand from excitation system, and because in the power plant you have the synchronous generator, and synchronous generator needs field excitation, the field winding of synchronous generator, to generate power, to generate voltage, and thereby the power, in fact. So the main function of the excitation system, and that we sometimes say exciter here, basically in a short way we simply say exciter, it will feed a DC current here to the field winding of the generator, and this field winding of the generator, it is placed on the rotor. So that means the field winding which is on the rotor of the synchronous generator, for its excitation, there is another system, and that system is the excitation system, or the exciter here. So this exciter will supply a DC current. All right, it will supply a DC current to the field winding of the synchronous machine. That field winding is placed on the rotor here. So here objective will be the control objective, right? The control objective will be to control the voltage. It will be the generator terminal voltage, and again the reactive power flow from the generator side. So because the synchronous generator in fact has apparent power as an output. So active power you get it from the turbine, and then it's mechanical power being converted into electrical power, but this conversion will take place in the presence of magnetic field which you have in the air gap develop. And then apart from that, you also have some amount of reactive power flow on the generator terminal. So in terms of control objective, it is to control the voltage and the reactive power flow on the generator terminal. And then last time we discussed about that the excitation system with the use of PSS, power system stabilizer, can also be meant to improve the stability of the system, and thus it is the excitation system which provides a source towards system stability improvement, that is to the stabilizer, power system stabilizer, because the power system stabilizer that feeds an external signal to the AVR section of the excitation system, and thus that's why here it is said that the excitation system can also improve the system stability here. Additionally, in more general, we can say that excitation systems performs control and protective function as well for satisfactory performance of your power network, by controlling the field voltage and thereby the field current. But here it is not because the effect of excitation system control action, it is mainly on the generator side, and but the satisfactory performance of the power system, this is, we have said, in context to stability improvement. Because if you want to say that controlling the field voltage and thus the generator terminal voltage, it is only on the generator side, because excitation systems cannot improve the voltage at other buses, right? It can only control the generator terminal voltage. That means the bus where we have the generator connected. It cannot be mint or it cannot perform for controlling the voltage at the other remaining buses in the network. So in that sense, I can say excited systems is only for regulating the voltage at the buses where we have the generator, and that is through the field excitation, the field circuit of the generator here. We have the protective functions in the system so that the generator operates, within the capability limits here. And thus, in that sense, because it is very much important that what is the capability limit curve of the synchronous machine, because the loading, because when we talk about the capability limit, it refers to the boundary, the region within which your generator will operate. So in that sense, because you have the loading on the machine, right? So when you have the loading of the machine, so up to what region the machine can be loaded, and that loading, when you talk about the current flow, stator current flow, it corresponds to the loading on the machine, and that stator current is it is a AC current, and it has both active component and the reactive component, and this is one part. And then we also have the limit on the active power flow or the active power loading on the generator based on what is the rating of the turbine which is connected to the generator. So again, there is a limit on the machine operation. Then
I have a question.
yes.
What the excitation system? You said the exciter provide DC current to the synchronous machine.
Yes.
Where is that current coming from? That power, is it coming from the grid, or do they use like a special
okay.
equipment?
Excitation systems provides the field current. So your point is, what will be the source for excitation system, right?
Yes.
Yeah. Okay. In for a small I have some discussion on this, because when you discuss the types of excitation system later on. So for a small excitation systems, we have a separate source. So that means you can have a separate DC source, which will the output of the DC source will be fed to the field winding of the synchronous machine, the main, right? So we have a separate exciter, actually separate DC source. This is one part. Another part, because instead of using DC exciter, we can use AC exciter, and again it can be a separate source. AC exciter can be separate source, but since if you have an AC exciter, it means the output of the AC, it will be a sinusoidal. Then you have to rectify it, right? You have to convert it to DC and then feed it to the field winding. So that is what we have it in a small size. Then for a big generator, for the case of big generator, we require more excitation, we require more field current, and such in the design of excitation system, we withdraw some power from the generator terminal, the main generator terminal. We withdraw power. That means from the generator terminal, we take out the power, and then we feed it to the exciter, and in fact, after conversion, and then feed it to the field winding. So that means we don't have any separate source for that. So it is the some power drawn by the same machine, and then it is being converted into DC and then fed it to the field winding. Yeah, this is what we do. Right? I will discuss that part later on, because we have different types of excitation system depending upon what is the source of excitation system. Yeah, right.
I see, but I'm talking like in practice, when you have a separate source, like what source do they use? Do they have like a battery, or for the small generators that you mentioned?
Yeah,
Do
that's
they
what I
use a
said.
battery,
So
or do they use?
yeah, battery will be a part of it. Battery will be a part, because let's say, for example, uh, if you do not have a separate source, then what will, let's say you want to start, all right, you want to start a generator. So initially, what will be the source for excitation, right? So in that case, the battery backup will be required. But if you have a separate source, then you don't require battery. But most of the cases we still use battery. Let's say if the excitation system fails, the separate excitation system fails, then we can provide the excitation to the battery in the initial stage. We can do that. So as a source, it can be as a DC source or it can be an AC source. That is, as a separate source, it can be, right? Right, Ibrahim?
Okay, yeah.
Yeah, I will discuss maybe a little bit more when we come to the types of excitation system. Right? Yeah. So as I say, as I was discussing, then the loading on the machine on the, I mean the generator, it also corresponds to what is the field of excitation, right? The field of excitation. And in that case, what is the amount of, what is the rated field current flow in the field winding? So that is again a limit. What should be the maximum amount of field current flow in the field winding? So thus, there is a complete boundary of for the operating region of synchronous machine, which is defined by the what is the maximum field current flow, what is the maximum active power, which is will be based on the turbine rating, and then what will be the maximum stator current with current flow in the stator winding synchronous machine. So there is a complete region for the uh, operating for the operation of the synchronous machine here. Uh, Here we have some of the requirements which we require for excitation system in operation, and they are as in the perspective of the generator operation and in the perspective of the power network operation. So what is said that in the perspective of the generator operation, what should be the requirement for excitation system? It is said that at a steady state condition, the excitation system should automatically adjust the field current. So it should not be done manually. All that. So that means whenever, let's say, the load, all right, whenever the load on the generator changes, so the terminal voltage will change. All right, there will be an error in the terminal, because we have to feed power to the load at a given voltage. And as the load varies, load changes, the terminal, I'm talking about the local point, right? If you have a load connected to the generator terminal locally, even in the case of large network, when you have, even in that case, it will be the same way. But so when you have a load change, so it will change the generator terminal voltage, and that has to be sensed. And just the voltage error, generator terminal voltage error, it is fed back to the controller, and then the controller in the excitation system should automatically adjust the field current of the synchronous generator. And so that means depending upon how does the output changes in a continuous form, all right? So that adjustment of the field current should take place automatically. This is one part. This is what we say at a steady state condition. Then even under when you have some disturbances, even under those situations when we have some disturbances, excitation system should be able to respond for the transient disturbance, I mean, right? So saying that if there was some load change or the line trip and so on, in that case also the excitation system should be fast enough. This is because Under a steady state condition, there is no disturbance, right? There will be some disturbance, it will be very small. So you can have the automatic adjustment of the field current under normal perturbations condition. But if there is some severe disturbances, which correspond to the transient response, right? Even in that case, your excitation system should be able to respond. So that means we want the performance of excitation systems not only against the steady state condition, but also against whenever you have some severe disturbances. So that means your excitation system should be fast enough. It should be that the time response, the delay in the response of the excitation system should not be much more. It should be very fast so that it can change the situation, and then as per whatever the need you have, or it can change the field current. Although, just see, uh, do you know that the flux, the field flux what you have in the air gap, do you think that it can be changed suddenly? What is your comment? Field flux
Probably
distribution.
not.
Field flux distribution. In
Probably
fact,
not.
yeah, there is always some amount of delay if you want to vary the field flux in the air gap of the machine. All right. So, but still we want that the field flux response, the change in the field flux response uh, should be fast enough so that it can uh, get the system restored whenever you have some disturbances. Then another one is saying that in both the cases, steady state as well as transient case, that thermal limits should be respected here. Because if you, let's say, you supply a very high amount of field current to the field circuit, right? So definitely it may result into heat development, because if you when you have a high current flow, field current flow to the field circuit, so it will have result into high heat development, and then the insulation may rupture. The dielectric property of the insulation that we have in the field winding, that may rupture. So thus this is also important. The thermal limits should be respected here. Next, when we talk about in the perspective of power network operation, it says that the excitation system should contribute, or it says up to some extent, right, uh, to voltage control. So that means it should be effective to control the voltage at the generator terminal and as well as thus the bus. Yeah. And also, most importantly, it should be able to improve the system stability. So what we now need, that so excited system should be able to respond quickly towards the disturbances so as to improve the transient stability. This is one part. And also, even if you have some small disturbances, even in that case, it should be able to change the field current in the field winding. So even not only for a transient condition, but even for small disturbances situation, even for that, the excited system should be able to meet the requirement for the improvement in the system stability. So thus here you can see the controller for excitation systems it is in fact in different way what we require for the generator operation and as well as for the power network. So thus it is excited system, it is very important here, not only for the generator but even at the power network as well. Yeah, right. Okay, so in general, this slide what it indicates or shows what are the subcomponents here, what are the different elements that an excitation system will include. So it is SYS, yes, it's control system. So what we have it here, it is shown as a block diagram basically. This is the generator. You have an exciter here, you can see. So the first element, it is the exciter here, this one. You can say the source, all right? The source for DC power. This is the source for DC power, which will be fed to the field winding of the generator here, right? Then the second part, when you refer, it is this one, regulator. Now that we call it as automatic voltage regulator. This regulator, as you can see, it receive, because we have different functions to be achieved through excitation system. So you can see that there are several feedback. There are several feedback here. And again, we also have a reference. So this corresponds to the reference voltage here. So it, in fact, this regulator will be basically the controller part, basically, where you will have the comparison of the error signal and then your reference signal here, and it will process some signal, and then it can also amplify the control signal, which is fed to the exciter here. So this will be the basically the controller for excitation system, which is in the cascade here. Next one is the third, what is the terminal? So this one. So that means it is the terminal voltage transducer and the load compensator. So you can see here that there is a feedback here from the generator output here. So there is a signal feedback, and it will be the voltage signal here. All right, there is a voltage signal feedback from the generator terminal, and it will basically help to maintain the terminal voltage. And in fact, it should be there is a, it should be actually 4, it should be the same at a remote point desired level. So that means this is the actual voltage measurement. This is the actual voltage measurement, and then it is feedback to the AVR section here. So this is third. Next one refers to the fourth here, the power system stabilizer. Here it should be fourth, the serial number. So now, if you refer to the feed power system stabilizer, here it is a feedback. Now, if you refer to the block diagram for the PSS that we discussed yesterday, so don't get confused that it is from, because here there is only one line shown, but here the state variable, the measurement variable, it will be either omega signal, angular speed, or the angle signal. Again, we get it from the generator terminal. So that's, so it does not mean that when I said, because for this case I said it will be the feedback of voltage signal from the generator terminal, but for this case it will be the omega signal and angle signal here, or angle signal here. So that PSS with the feedback of angular speed or the rotor angle signal, it will have a signal that will be the input signal to the regulator, and that signal is your voltage signal here, which will be required to damp out the system oscillation. So thus it is the stabilizer which feeds a supplementary signal here to the regulator, because this regulator and the excited systems, they get us one feedback signal, that is the voltage signal, and then they correct it based on the reference signal here, that is the voltage signal. But PSS also provides, I said, supplementary signal. So it is the voltage supplementary signal which is feedback here, and but the objective will be to damp out the oscillation here with the stabilizer signal, which is a voltage signal being fed to the regulator here from PSS. Next one, what we refer here, it is the limiters and the protective circuits. This is the fifth one. Now these are basically the protective part here. We have the protections, relays here, and so on, because we want our generator, we want our excitation systems to operate in the boundary, that means in the region, operating region, and thus there should not be any violation of the capability limits. So thus this part refers to the protective circuits or the limiters, such that the field current or the field current flow from the exciter to the field circuit, or the static current, that is the loading on the generator, they are within the limits. Yeah, and thus that should not be exceeded. Those quantities should not be exceeded. So thus we have the protecting here. So if it crosses, then this the relays in the circuit, they will tip the generator. Yeah, and thus they can uh, prevent any damage occurrence in the generator here. Right? Anything on this slide?
So the regulator regulates the voltage, right?
Yeah, regulator is actually, you can say, the controller for the excitation system. Yeah, yeah. It
And what
regulates
is
the.
this remote point at desired level? You mean, is there another measurement or?
Okay. Yeah, in fact, again, remote point, because it is not only the generator terminal voltage, right? Because you get a feedback here. Now, let's say this generator is connected to bus 1 here, and then let's say you have some another bus here, right? And this is to the line. And again, in some cases, right? But in some cases, for more fine control, I can say, we can have the measurement of the voltage signal at this bus and then fed it to the regulator here. And then it will improve the voltage at this point, and then the voltage along the length of the line. That is possible. But it cannot be at a widespread network. It can be only the adjacent buses. Let's say, for example, if I say, let's say you have one bus here, then it is connected to another bus here, right? And then you have another bus here, and then you have the connection here. So here you have your generator, right? This is a generator. Right. So this is the bus 1, bus 2, bus 3. Now, if you want to say that, okay, you here you have some voltage, right? You have the load here also. You have the load here also, right? Now, let's say that this is the voltage V1 and this is the voltage V2. And let's say you want to maintain 400 kV on these buses, right, in the network. Now, if you find that because of the load change here, you want to regulate the bus voltage here, right? Now, in some cases, it is possible that you send the signal information from this bus to the AVR here, and then regulate the bus here, and thereby for the entire line. That is possible. So what I mean to say, it can be possible to regulate the bus voltage for the adjacent ones. But if I say this is far away, right? Some another part of the network, much farther away, there it may not, because it is possible that this bus is not connected through this one. Because for when you talk about the remote, there has to be signal transmission, right? And so in some cases, the substations in our network, they are connected to the optical fiber cable, basically. So if you want to regulate the bus voltage for the adjacent bus here, then the signal information can be, the measured bus voltage can be transmitted to the optical fiber cable, and then this excitation system over here can be regulated so that the voltage along this length of the line can be improved, and thereby on the bus here. So that is possible. But here the remote means it is only for the adjacent one, but not away, no, not for the far away buses, not for the far away buses. Let's say you have several intermediate buses here, right? So then for this bus, it is difficult to regulate the voltage just by using this excitation system, which is here, right? Okay. This is what it refers. So bus voltage regulation, it is possible through the excitation system, but either at the local level or for the adjacent buses only, but not for the remaining buses which are far away. For that, we require some compensators. So it could be in the form of capacitor bank or the inductor bank. And those compensators will be meant to regulate the bus voltage here. That is what we do, right? It is not entirely to the excitation system, okay? Because the amount of reactive power which is from the excitation system, that I can say a little bit somewhat lower than with the use of compensator bank. Yeah. Right. So let's say, for example, you need something 300 MVAR. So excitation systems, they cannot provide you 300 MVAR, right? So that has to be met by your compensating bank only through capacitor banks or the reactor bank only. It cannot be from your excitation system, because your network, just say your network is completely inductive, right? And your loads are inductive. So thus, just by having one excitation system, which is at the generator, you cannot provide all the reactive power demand in your network, because your line is inductive, your load is inductive, right? So just one exciter systems cannot meet all the reactive power demand from your in the network. So for that, we need separate separate compensator bank here, right? Is it agree, Ibrahim?
Yes.
Okay. So yeah, so here I have this slide to discuss what are the different types of excitation system. And I will not go into more detail. You can refer the book by Kundur and the section 8.3. But as Ibrahim, you had one query. So what will be the source? So as you can see, this is the most basic type of excitation system, and this is DC excitation system. And as you can refer here, this is the stator of the main generator, that is the synchronous generator here. This is the stator, and the stator will have the terminal voltage here, right? And this is the field winding of the main generator. And you can see here that this field winding, this is the excitant, the field winding, right? This field winding has to be excited by an source. All right. And you can see here that there is a slip ring, because it requires what to have it here, the fields winding, right? So it is has a slip ring, and then here you have a separate source here. So you can see there is a separate source, and that separate source is your DC exciter here, right? And now in the case of DC exciter, that is basically the DC generator. So this is basically the DC generator, and the output of the DC generator, this is the armature here, right? And in fact, if you know, for the case of a DC generator, this armature, it is on rotating one. This armature is rotating. However, the field circuit is in stationary, right? So this is in rotation, and the output of the armature of the DC generator, that provides the field current to the field circuit of the main generator here, right? Then you can see that again, what will be the source for this one, right? So this is the main generator is exciter. To excite this field winding, you have DC exciter. Okay, so it is this armature which will excite. Now, what will be the source for field winding of this exciter? Again, we have here, you can see it is basically again a source here, that we call it as amplidyne. So this amplidyne, it is basically like it is actually a DC source. It is a DC source, but it has several stages of amplification, right? And thus you can see that with a small signal, right? With a small signal of the voltage, which you get it from the main exciter, we get it from the CT and PT through the regulator, and then again we can have some amplification here to the field circuit, so as to excite the output stator terminal of this one here for the amplitude. So with a small voltage of field excitation, its output is amplified, and then it can be used to feed the field current over here. So that means even the DC exciter as shown, it requires another amplification or another source for exciting this field winding here. So this is what we have it for the case of DC excitation system. Now, this is shown with the amplifier, but in some cases, this is the amplitude is not required. So what could be the another source here? Yes.
Can the DC itself self-excite itself? I know that.
Yeah, it
right?
can be self-excited. Yeah,
Yeah.
but again, let's say if the self-excitation fails, then
you need a battery.
Then you need a battery. So in some cases, normally, because I mean those generators, synchronous generator, which are driven by diesel oil, right? Have you heard of the diesel engine generators?
Yeah, of course, diesel generators.
So those could be of capacity. How much? What could be the maximum capacity of the diesel generators? Maximum 50 MVA, right? Maximum.
I don't
Yeah,
know.
it could be something.
I'm familiar with the small ones that we use.
Okay. So that could be the maximum size, I say, and then so. But if you say shorter capacity, it could be, let's say, 1 MVA, 2 MVA as well. Right. So in that case, we don't require this one. So we may have a use of battery and then another DC exciter for exciting the synchronous generator here, field circuit. So that is possible. This is one part. Then another one which we refer here, you have the generator, the main generator. This is the field winding, yeah, and this field winding of the main generator is excited from another DC generator. This is again a DC generator here. In fact, it's a block representation. It is shown here, block diagram representation. So this is the armature here, which is shown, and then the field excitation of this DC exciter, it is to the amplifier here. So it is this one, right? And then you can see you may require stabilizer circuit here because that will form the automatic voltage regulator part here. So we may have stabilizer, and then again you can see with the measurement of from the generator terminal, we have some rectification and then fed it over here. So that is the in fact the block diagram representation for the DC exciter system here, right? Now, in fact, it is important that if you refer to this characteristic, right, and on the x-axis you have the field current here, right? So that means what is the excitation level, or if I talk about for the generator terminal voltage, so what is the excitation here? What is the amount of field current here? So I mean to say, what is the field current over here? And then what is the voltage? We get it here. So that means this is your field current, and what is the open circuit voltage here, right? So here on this x-axis, it is the field current here, and then on the y-axis, it is the open circuit voltage. So what is the relationship? How does you vary the field current, and how does the voltage, open circuit voltage, will vary? So this is what is shown here, right? And you can see that in the initial stage, right? In the initial stage, in fact, the real generator characteristic, this sometimes we call it as MMF characteristic here. MMF characteristic, we say, in fact, we can say sometimes open circuit voltage characteristic, open circuit voltage, because we will measure open circuit voltage and the variation of the open circuit voltage with respect to the change in the field current here. So because this axis is the field current here. So how does the open circuit voltage will vary when we change the field current? So in general, what we observe that this is the characteristic we get. Yeah, this one. So you observe that for the initial part here, right? Let's say up to this one. Okay, you can say that it is a linear relationship. As you vary the field current, you get open circuit voltage here. But for a higher amount of field current flow, for this range, when you say for higher amount of the field current flow, you don't find corresponding increase in the open circuit voltage, right? So that means there is at least beyond a certain range, beyond up to certain range, you get a linear curve, you get a linear relationship between the field current and the open circuit voltage. But beyond a certain range, beyond this limit, the curve becomes saturated, and thus you don't find corresponding increase in the voltage with a increase in the field current here. So thus, when you have to model the excitation system, it is important to model the saturation part here. It is more important to model saturation part. Linear part is okay because for the normally the synchronous generator, they will be operating at a rated voltage, and when they operate at a rated voltage, they are always overexcited. And when they have overexcited, that means you have the field current little bit higher side, where the machine operation is towards the saturation region. And in that case, it is important to model the saturation curve for the excitation system. That is most challenging in the modeling of excitation system. That is the accurate representation of the characteristic that is mainly in the saturation region of the curve. Yeah. Right? Because we have to control the voltage here, right? We have to control the voltage here. So what should be the change in the field current here? All right. So how much change in the field current you should have, delta change, how much should be the change in the field current you should have, so that you can have change in the open circuit voltage here, right? This is, and again, this is open circuit. That means the generator is not loaded. But when you load the machine, then again this voltage will change. All right. So because there will be a current flow in the stator here, so this voltage will change. So it is important that the terminal voltage at the loading condition, how it changes with the field current. So that is again another part how we are able to maintain achieve a relationship between this voltage, terminal voltage, and with the field current here in the exciter modeling, right? Here we have some other types of excitation system, and in this case you have AC type, right? And if I refer to this one, this is your main generator, right? And this is the stator, this is the field winding or the main generator, and the slip ring, and then you have a diode. Now in this case, the separate source, it is an AC, it is not a DC in the previous case what we have it here. So we have the use of an AC exciter, but since it is a AC exciter, its output, right, it is now rectified through a diode here. It will be a complete diode bridge circuit here. Diode bridge circuit which will feed the field current, DC field current, to the field circuit here. But again, and what about the excitation for this AC exciter? So again, you can see here from the generator terminal. From the generator terminal, you get some signal. You get some signal through the regulator part because we want to control the voltage, and then control the voltage based on what is the requirement of the field current. Based on that, here you can see it is rectified. So in fact, it is some part of the signal, some part of the power from the generator, from the main generator, it is drawn. It is drawn here. It is, in fact, you have some regulation here, and then the signal is what you find it here. It will be controlled, and then that signal is then fed here. So, what is the amount of DC excitation to the field circuit over here? It is being controlled through this loop, and again you can see that the output of this one, it is fed here. So that means some power is drawn from the main exciter, which is rectified, but the amount of power drawn from this side, that is being regulated with the outer loop here. So in fact, see, so that means this excitation is regulated in two loops. One is this one, another is through this one here. So we have what is the amount. So thus we have more effective approach in the regulation of the field excitation over here, and thereby the field circuit over here. So that is what we have it in the AC type. Then we have another one. It is the brushless excitation system. So you have an armature, the main generator, the field winding here, and the field winding has to be, this is again, it is a bridge circuit, that bridge circuit here to supply the field current, DC field current to the field winding. And here you can see that there is a AC exciter here, right? And that AC exciter will supply the field current, and its excitation, the AC, in fact, AC excitation, that is through another field circuit here. And then again, you see that for this part, you have another one. There is a pilot exciter here, and that pilot exciter, what you have it here, it is actually the field circuit. This is the, you can say, a small generator here. This is also a generator. This one. This is also a generator, and this is also a generator here. So this is the one which is exciting the armature here, and then this is the pilot exciter. This is the armature of the pilot exciter, and which will be regulating. And then, in fact, what will be the source for excitation to the field winding over here? So it will be through this one, right? So this is something like what you call it a brushless excitation system. Yeah. Right. So this is under the category of AC type, both of them. And if we refer to the, which we normally use for a large generator, normally use it for the large generator, there we have static one. Because here you can see, because this is the rotating component here. Then again, you have this one rotating component. So as such, we want, because since we want fast response from the excitation system, and thus it is preferred to have the removal of those moving parts in the excitation system. And thus this one refers to static one, where there will be no moving parts in the excitation system. So as you can see, this is the main generator, stator, that is the armature, the field circuit through the slip ring, and again through the bridge circuit here. So you just have, you can see, yeah, the some amount of power from the generator terminal. It is withdrawn, fed back, and then it is step up. It is step up. That means a small amount of signal. It is step up here, and then rectified here, and then fed it to the field circuit for the main generator. Then you have some controller part, regulator part here. So for this, how much should be the amount of excitation in the field winding? So that is controlled through the bridge circuit here. So this main generator, what you have it here, it will be through the step down transformer, right? And it will supply power to So this is basically the stationary. This will be the stationary rectifier, and it is regulated by through the control one here, regulator here, and that's why we call it as controlled rectifier. Yeah, this one complete. And these static rectifiers will supply the exciting current to the field winding, that is to the slip ring here, right? Anything on this? So now I think it's clear that what will be the source for excited systems, how we achieve the power required for exciting the field circuit of the main generator.
Yeah.
Yeah.
It's more clear now.
Yeah. Okay. Should we have a break here for some few times, sometime? How much?
Yeah, I think that
3
would be
minutes?
good.
Yeah. Yeah. Okay. Okay. For 3 minutes. Right. So we move to the next slide now. I hope you can see my screen, right? And, yeah. So here we just now, in fact, we have different types of excitation system, and DC type of excitation system. And as I said, that it is important, more important that how well you are able to represent the accurate characteristic between the field current and the open circuit voltage on the generator terminal. That is more important in the modeling part. And we have different types, as I said, AC, DC, ACA, and static one. But you can see in the case of static, there is no rotating component. And thus, as such, the model of different types of exciting system could be a little bit different. But when you talk about the modeling, so we need to go through the modeling of several stages in the excitation system. And here I will discuss the simplified model for excited systems, or the AVR model. So we'll start with a sensor, because sensor will form a special main component, in fact, which will be used for measurement of generator terminal voltage. So you get the measurement of the generator terminal voltage through the potential transformer, and then which is being fed to the regulator part. And this signal, it is through the bridge circuit here. So thus we need to model the sensor here. So this is, and you can see the output voltage signal for the sensor. And this is the generator terminal voltage. So the ratio of output of the sensor and the input of the sensor. So input is the generator terminal voltage, and output is the sensed value, the measured value. And this is how we define it. So the sensor can have some gain, right? It can have some gain, and it will have some time constant. So it is this quantity which represents the time constants for the sensor dynamics. So because let's say that you have some signal, right? You have some voltage signal here, right? It could be, it is the voltage signal here. So this is, let's say, delta VT signal. There is some change in the generator terminal voltage, and let's say that it is a step change. So let's say this change is by 0.02 per unit, right? It is in per unit. So this is the change in the generator terminal voltage in per unit. Now, what will be the change in the measured value of the voltage signal from the sensor, right? So it could something like, because this is a first order model, so its output response will depend upon this one, right? So that means the sensor, it is actually modeled as, this is a sensor here, sensor model. Here the input is your delta VT, and the output you get it as I can say delta Vs. So for the change, for the step change, what you have it here. For the step change, you have it here. What will be the corresponding change in the voltage at the output of the sensor? You get it this one. So this is how we have model the sensor. It is as a first order model here. Similarly, when you look at amplifier, again you can see from the this case here we have amplitude, right? Amplitude is as amplified. So this amplitude, it is again a rotating component here, right? And then in this case we don't have any amplifier, but the regulator which we have it here, it will have a static amplifier. All right, it will be a electronic circuit as amplifier here. There will be here also, same way over here also. So but again though we don't have in the for this type and static type, we don't have rotating amplifier, but still there could be some time constant involved with the amplifier as well, and thus the excitation system amplifier, as I said, a magnetic amplifier. So the amplitude what we have it here, it is a magnetic amplifier. And then for other cases it could be like electronic amplifier as well. So this amplifier is now represented with a gain this and with the time constant, and thus the input signal to the amplifier, the input signal to the amplifier and the output voltage of the amplifier. So this is how we represent it. So this represents the time constant of the amplifier here. Next one is the exciter. So because here this is your exciter, or it could be this exciter, or as in this case it is only this one. So because the static one, it is only the rectifier part, but if you refer to DC, so it is this exciter. Now how to model these exciters here? So that is again in a simplified form. We have considered a linearized model, which in fact has a major delay, major time constant, a higher comparatively time constant. And if we neglect the saturation and the non-linearities, then we can represent it by first order model for exciter model, exciter system. So it's the gain of the exciter and the time constant here. So in a more simplified form, we can have the complete representation as consisting of sensor, amplifier, and exciter here itself. Anything on this part? No? Okay. So then again, there are some more components here, but this is in terms of controlling the exciter basically. Here we talk about the exciter system, so the main devices, but control part component wise, it includes transducer and the load compensation circuit here. Now this one we represent it by a single time constant and with a unity gain here. So you can see here that the transducer part, it is represented by a unity gain and one time constant here for the transducer. And then again, because for the improvement in the exciter performance, we have some compensation in the voltage signal, and because there will be a, because the entire exciter systems will impose as a load, and that load is modeled as this series impedance, and thus how to compensate the voltage drop across the exciter elements itself, and that is the compensator we have included here. So it will be based on what is the terminal voltage from the main generator and the current, and then this is the you can say the compensating voltage signal which is added here. right? So with the through the transducer and then given to the AVR part, because this is the reference voltage and this will be the error signal there. So the measure voltage which you get from the generator terminal, it will be through the transducer, but with some compensated voltage included in the circuit here, right? The next one refers to the main regulator part, because once you have the error signal, it has to be controlled. So thus the regulator will have an error signal. So as you can see here, so this is the error signal, which will be after this one, right? And as you can see at this point, there could be some stabilizing signal that will be from the PSS, you can say, or there could be some another feedback signal here. And then this is the regulator, that is the controller. So thus here we have some compensator stage, and that compensator stage is basically lead lag compensator, because we want to either provide a phase lag or the phase lead to the voltage signal here. So thus we have a lead lag compensator, which will be as a part of a regulator here. And then here you can see the exciter representation. So it has some gain, amplifier gain, and the time constant. But again, there is a limit here. So what will be the amount of voltage regulator quantity? So that is again within the limits defined by here, the limiters here, right? Anything on this part? Okay, so we move to the next one. So yeah, this is if you refer here, we discuss about the this one, and yeah, next one. So now for the, as I said, that we want improve performance for excitation system. So here we have another circuit, a stabilizing circuit for excitation system, and its block diagram is shown here. So you can see that this is from the generator field winding. So because this is your automatic voltage regulator or exciter here. The complete representation, what we had it here, this one, and this, in fact, basically this one. So this is included over here. And then the signal, what you get it from the exciter, it is the field voltage, which is given to the field circuit of the generator. Here there is a feedback. So in fact, this is referred as feedback compensation, and then its output is given to the reference voltage. So if you refer in this block here, so this one is the stabilizer feedback signal. So we get it here. This is the stabilizer feedback signal, which that means here we have several loop basically in this circuit, in the regulator circuit. One is through this one. So this is the stabilizer feedback voltage, which is given over here. Because I think we have referred earlier that AVR has, because with the inclusion of AVR in the circuit, instability situation may arise, right? Do you remember when we are discussing yesterday SMIB system? Yeah.
Yes.
Yeah. So in some, because first part yesterday we have discussed SMIB, then with SMIB with AVR, and then the SMIB with AVR plus PSS, right? So when we have the AVR, so there could be a situation where instability may arise, and that instability is because of poor dynamic performance of excitation system. Why poor dynamic performance? Because we have several delays here. because when you look at this one, sensor model, again, it is a first order delay. Amplifier, again, as a first order delay. Exciter model itself, first order. But again, this is what we're saying. It is a most simplified model representation. But if you take more non-linear model, then there will be a higher delay introduced. And thus the dynamic performance of excited system, it is comparatively poorer. And this is, it is mainly for DC and AC types. Because if you refer to DC and AC type, because this is the DC, you have a rotating component. And thus the time response for a DC exciter system, it is much slower. Similarly, if you refer to the AC type, again, it has a rotating component. Again, in this case, a rotating component. So that thus the time response for these two types, they are much slower. But for static, we don't have any rotating component. We only have rectifier. So thus, this type of exciter, static exciter, can be much faster. So this problem, what we have, it is mainly we observe in the case of DC and AC type, because they have much higher time delay. For that, again, if you remember that we have, if you for yesterday when we discussed the one of the numerical problem for a certain range of the gain, right? The synchronizing torque coefficient and the damping torque coefficient, they were positive and negative. Am I right? If you remember yesterday, for some of the values of the gain that we have considered, the synchronizing torque coefficient and the damping torque coefficient, they were positive or negative, right? So if you have the amplifier gain too small, then this AVR response may result into unstable. So thus, for these situations, we want an improvement in the exciter response here. And for that, we have this stabilizer circuit. So there is a stabilization which is provided here. In this case, we have a feedback. In some case, you may have a series compensation provided here itself, but as shown in this case, you have a feedback. So this compensation is provided in the feedback to improve the dynamic performance of the regulator system. So what it does basically, it is nothing but a controller, because this compensation is nothing but a controller here. And you can see, because if you hear it in the numerator part, it is S times Kf. So Kf is the gain basically, you can say. And divided by, in the denominator, it is 1 plus STF. So Tf is the time constant here. So if you don't have S, it means it is a first order system, right? With only a pole here, with only a pole. But in the numerator, there is one S here. So it means it will add a 0 to the AVR, and thus it will compensate the delay part here. So with the 0 addition, which you have in the numerator, we can have more phase margin in the frequency response. That is the Porte plot. Have you studied the pole and the zeros in your control system course?
Yeah. So
okay.
The poles in the
zeros,
denominator, okay, and the zeros in the numerator.
Yeah. So with the having 1 0 in the numerator part, we can have more phase margin, and thus we can provide good compensation. So this compensator minimizes the phase shift, and which we have it because of time delay. Because with the time delay, with the last time delay, that means the response gets slower, because if you have some step signal here, and it is well desired that your response should be very fast. It should be this one. This should be your desired response, right, for any controller design. But if you have several time delay involved, your response could be delayed this way, or maybe a little bit faster. It could be something like this. It could be, right, or a little bit faster, your response could be this one. So, but still, this is the amount of further this is the region where the response it is delayed here. That means up to this time period. It is at this time period the controller response is delayed basically, and thus we need to compensate this much delay in your response. And here we obtain it by adding 1 0 here, and thus it minimizes the phase shift here. And this can improve the stability here. Now, but here how to add a 0 to AVR here? That is said that we can add a rate feedback to the control system. So that means how to design the value of K, because addition of 0 in the S plane will depend upon what is the, because this will represent a pole, 1 by TF will represent a pole, and this KF will represent a 0 in the S plane. I mean, if I take this, if I remove this, for example, let's say you have a plane here, right? And let's say you have a pole. So this is your pole here. So this pole will be 1 by TF here, right? Now, where should be 0 located? And 0 located will depend on what is the value of KF here. So that means whether your 0 should be on this side or it should be on this side. That is important here. So the 0 location, and that could be adjusted by setting the value of KF and TF here, right? And in some cases, we can provide a transient gain reduction, and that is again a compensator. So we can have a lead lag compensator here. So that is also possible over here in some cases, right? So this is again given in detail for the stabilizing circuit for excitation system. So what do we have basically? Because this is the armature of the exciter here, main exciter. So it could be, for example, for this one, AC exciter, or it could be from here, or it could be from DC exciter here. So you get the signal from the exciter. It could be DC or AC measurement signal. So this is the transformer here. So you step up, because this will be the error signal here, feedback, and then you step up the voltage. You get another feedback error signal from the main generator terminal, and then here we have the difference of the two, this signal and this signal here, and then this is being amplified and then fed to the field circuit or the main exciter. So that could be we have represented what will be the voltage here, written down the voltage, and what will be the voltage on this side. So this is written down in terms of KVL law following the transformation ratio. This is in terms of self-inductance of the transformer, and this is the mutual inductance of the transformer, and this is the resistance of the primary side, and this is the resistance of the secondary side. And we consider the secondary of the stabilizing transformer to be high impedance circuit. So with this assumption, we write down the equation here, we simplify this one, and then finally write down what is this ratio, and it is in terms of this one. So it is the same, in fact, yeah, because this is the stabilizing circuit transfer function, and how this equation is derived, it is here actually. So this is the ratio of VF to EFD, and what is KF and TF, so it will be this one. And thus how, as I said, that how could we can have the placement of 0 and the pole, that will depend upon what is the time constant here, TF. So, and what is TF? That is the inductance here. The inductance of the primary side of the transformer and the resistance of the primary side of the transformer. And then the KF is the gain. This is the mutual inductance and the resistance of the primary side. So that means with the setting, with the impedance value of this transformer, we can have this feedback compensation design here for the stabilizing the circuit. Right. This is what we do in normal circuit design here. So yeah, this is what is shown. So the complete exciter model. So we have this is the exciter 1 by k first order. Then again here it includes the nonlinear part modeling. Then we have a feedback from the stabilizing circuit part here, which is fed back to the reference voltage. This could be signal from the PSS, and then the regulator part. Here it refers to the gain of the regulator, and then the lead lag compensator for the regulator. So the overall block diagram for the excitation control system could be something like this here. But this is again in general representation here. With so you can see we have combined. If you start from here, we have not shown the sensor part here, but we have shown the amplifier, we have shown the exciter here, and we have not shown this one in the feedback, but the regulator part, we have the lead lag compensator and the regulator amplifier gain part. We have, and then the feedback compensation part. So we have it here. So this is the feedback compensation. This is the stabilizing circuit, exciter model, amplifier gain representation, then the compensator part here. Right. So maybe I stop here.